In this video, we're going to go over graphical representation of simple harmonic motion. So in the first 2 minutes, we're going to go over concepts, right? So important formulas that you should keep in mind. And in the rest of the video, we're going to go over 3 really representative, really important examples that might show up on your quizzes and tests. So let's start by firstly looking at this formula right here. So we have an equation for the position of the oscillator. Remember that oscillators are essentially things that just move like back and forth. So typically in this class, we have 2 types of oscillators. We have either a pendulum, right, that is moving like back and forth, or we have a spring or a mass that is attached to a spring. So it's essentially oscillating right to the left, to the right, to the left, to the right. So X would represent here the position of the oscillator at the unit of time t, right? So we basically have an equation here that describes position as a unit of time t. The other variables that are involved here are the amplitude of the motion. So this is the maximum that, for example, the spring could be extended. We also have angular frequency, which is how many degrees the oscillator moves per second, or radians per second. So you can write this formula either in terms of omega or in terms of linear frequency. So linear frequency is measured in units of hertz or per second. So it's how many oscillations you do, right, per second. In other words, you can understand frequency as imagine if you're standing on a shore and you're counting how many waves are arriving at this shore per second, right? So you count it's 5 waves per second. What you just calculated is your frequency. As you can see here, right, the omega is just equal to 2 pi f. So you can calculate between the angular to the linear frequency using this equation. And you can also, from your frequency, you can calculate the period, or you can calculate period from the angular frequency as well. So essentially what we have here is just a cosine formula, right? So if you're already very comfortable with plotting cosine functions, this should be pretty easy. Or if not, if you're not comfortable with it, it's going to be a pretty good review. So if we have the position of the function of this oscillator as a unit of time, remember one period of cosine graph will essentially look like this, right? Then after this, the function is just basically oscillating back and forth, right? This is why these functions, the cosine function is a good representation of an oscillator, right? Because an oscillator is essentially going back and forth. So the half of this total height right here is going to be the amplitude. This right here is going to be the period, right? Because it's the time it takes for it to go back to the same exact point. So essentially we have this plot. Now let's take a look at our first problem that has to do with this equation. Here we have a certain mechanical system where a piston executes a simple harmonic motion where its displacement from the equilibrium position is given by this function. Now determine at t is equal to 0, determine the position of the piston. So all you have to do for part A is just plug in 0 for t. So we have an equation 4 centimeters times cosine 3 pi. So instead of t right here, I'm going to just plug in 0, since we're looking for the position at the time equals to 0, plus pi over 3. So 3 pi times 0 will just be 0. So 4 times cosine of pi over 3. Cosine of pi over 3 is equal to 1/2. So this is going to be equal to 2 centimeters as our final answer. So as you can see, it's a pretty straightforward process, right? We just plugged in 0 for the time and solved for our position. Now for part B, what is the period and the amplitude of the piston's motion? So here's our formula over here, 3 pi t plus pi over 3 that we have given here. Just to remind you, the basic formula, right? The equation that you would find on your equation sheet is this one. So So we just have to match our equation with the formula that we're given. As you can see, amplitude, right, is this number in front of cosine. So amplitude is simply equal to 4 centimeters. Now, period is not directly given in the formula, but what we can find, right, is this is omega, which is the angular frequency. Omega is equal to 3 pi. And from omega, we can find the period, which is 2 pi over omega, or 2 pi over 3 pi. So the final answer is 2/3 seconds. So as you can see, a lot of these problems is just going to be like matching the equation that you're given in this problem to the equation on your formula sheet. Hopefully this was pretty straightforward. Let's practice doing these things on this next problem right here. So here we have another harmonic motion problem. We have now a 2 kilogram particle that is undergoing a simple harmonic motion according to this equation. So 5 cosine 2t plus pi over 4. Now, in this equation, distance x is measured in meters and time t in seconds. Determine amplitude, just like before, right? So actually, I want you to, so here's the formula for, here's the formula that we have from our equation sheet for position x at a time t. I want you to think, what is the amplitude of this motion? Just like in the previous equation, right, we just have to match the coefficients. This number in front of cosine will tell me the amplitude. So amplitude is 5. They say it's measured in meters, so 5 meters. Then we can also see that the number in front of t will give me angular frequency. So angular frequency is 2, and angular frequency is given in the units of radians per second. Just like before, right, I can calculate period from the angular frequency. So 2 pi over omega, or 2 pi over 2, gives me the period of pi seconds. Fantastic. And I can find the frequency. Frequency is given as 1 over period, which is 1 over pi, and it's given in the units of hertz. Okay, so as you can see, pretty straightforward process, right? You're just matching the coefficients to the formula and then calculating the rest of the quantities from them. So in this case, we had to calculate period and the frequency. Great. Now in part B, we have to calculate the spring constant associated with this motion. So another formula that you will find for simple harmonic motion is the following, that omega, which is the angular frequency of the spring, will be proportional to square root, or will be equal, I apologize, to square root of k over m, where k is the spring constant and m is the mass that is attached to the spring. So what we need to find here is k, right? Because we know the mass is 2 kilograms and omega over here, as we found, 2 radians per second. So let me plug everything in. Omega is 2. Mass is 2 kilograms over here. So I just have to rearrange for k, square both sides. So squaring both sides will get rid of the square root. And multiply both sides by 8. As you remember, the units for the spring constant are newtons per meter. Always have to remember our units. And just like this, we solved our second problem for this type of simple harmonic motion. Now, let's move on to the third problem, which is going to be maybe even more important than this one, because in this third problem, we're going to look at the graph of simple harmonic motion. So right here, don't be scared by the amount of words. In this lab experiment, a student investigates harmonic motion by attaching an object to a horizontal spring. The setup allows the object to oscillate back and forth along a frictionless surface. All of this so far just describes a very generic example of an oscillator. To analyze the motion, the student utilized position sensor, which tracks the displacement of the object from its equilibrium position over time. A graph summarizing a segment of the collected data displays the oscillatory pattern clearly. So essentially, here's the graph of the oscillations, right, is what it's saying. So we have a graph of displacement in the units of centimeters versus time in the units of seconds. So we have to find all the quantities that we had to find before, but now instead of using an equation, we have to use a plot. So for part A, we have to find the frequency of the oscillation. While I cannot read out the frequency directly from the plot, what I can get is the period. The period of the cosine graph is going to be just the time it takes for it to complete one complete wave. So from here to here. The time that it takes is, as you see, 0.8 seconds, right? So therefore, the frequency, which is given by the formula 1 over period, is going to be 1 over 0.8. Which is equal to 1.25 hertz. Great. Just like this, we solved part A. What about the amplitude of the oscillation? What is the amplitude of this graph? as you remember, the amplitude of the graph is like half of its height, right? So this is going to be the amplitude, which is given as 2, right? You can either just like label the half of the graph, or you can find the total height, which is 4, and divide it by 2. So reading off from the graph, the amplitude of it is equal to 2 in the units of centimeters. Finally, as a final equation, we have to write a final equation that describes the position of the oscillator at the point of time t, right? So we have two equations that describe position. A is equal to cosine 2 pi f times t. So we just have to plug in A, which is 2 centimeters, and for f, we have to plug in 1.25. So x is equal to 2 cosine. Let me just simplify this a little bit to multiply 2 times 1.25, which is going to be equal to 2.5 pi times t. And we have here our final equation for the position of the particle at time t. Fantastic. In the next video, we're going to start going over rotational motion, essentially the last unit of physics, the last unit that we'll go over in this class. It's a very, very important unit, but if you have a grasp of the previous units, this should be pretty clear. So keep practicing and keep watching these videos on your way to an A. Thank you guys for watching as always.